So thank you for allowing me to come and speak. I am Jennifer Hardwick and I'm over at the University of Western Australia with ICRA, and I've just started my second year of my PhD, so I'm supervised by Luca Cortez and Daniela Breshkov. So angular momentum is an important quantity to study as it's linked to a galaxy's formation, evolution and morphology. In the early universe, dark matter halos obtain their angular momentum through tidal torques. Later, gas will fall into these dark matter halos, kinematically mixing, and then later when they collapse, some of this angular momentum will be lost. From cold dark matter theory, we can obtain a relationship between the mass of a dark matter halo and the specific angular momentum of that halo. This can then be converted to a relationship between the stellar mass and stellar specific angular momentum, where now we have these two extra quantities in here, Fj, which is the fraction of stellar specific angular momentum retained by the stars from the halo, and F star, which is the stellar mass to halo mass fraction. So you could say that the relationship between stellar mass and stellar specific angular momentum potentially has the possibility of giving information about how angular momentum is transferred between dark matter and the enclosed galaxy. If you make the simple assumption that these F star and F star parameters don't vary as a function of mass and that they're constant, then you can get the simple relationship that the stellar specific angular momentum is related to the stellar mass to the power of 2/3. Now you might think this is quite a simple assumption to be making, but this was actually what was found by Fall in 1983, where he found this relationship of 2/3 between stellar specific angular momentum and stellar mass. And because of this foundational work done by Fall, from here on I refer to this as the Fall relation. So down here I show the some follow-up work that was done by Romanowski and Fall in 2012, which again shows that you can see galaxies following a relation of slope 2/3, where here we've got disk galaxies and elliptical galaxies following parallel relations, both with a slope of 2/3, but they are offset with the elliptical galaxies having 5 times less specific angular momentum than the disk galaxies. So many works have found a slope of 2/3 in this relation. However, not all works have found this. For example, Posty et al. In 2018 found a shallower slope for their data, where they specifically found a slope of 0.55. And in this work, they claim that this maybe favors a different way of dark matter and galaxies imparting their angular momentum on each other. And in particular, they claim that this might favor a bias collapse model. We also see in this work here that there is a less of a dependence on scatter on morphology. What all these studies that have looked at the Fall relation before have in common is that there is not a large amount of statistics for these. Not more than 100 galaxies usually have been studied. These also tend to be dominated by H1 rich galaxies and often don't cover a wide variety of morphologies. So in this work, we hope to address this question by looking at a larger, hopefully more representative sample and see if this affects any of the Fall relation features. So this is where XGASS comes in. XGASS is the Extended Galax Arecibo SDSS survey. It's a survey of 1,179 galaxies where they're only selected in stellar mass and in redshift, where the stellar mass is between 10 to the 9 and 10 to the 11.5, and in the redshift range of 0.01 to 0.05. So these galaxies are all observed in H1 until H1 is either detected or a gas fraction limit is reached of 2 to 10%. So that's what you can see over here on the left, where you've got a range of stellar masses between 10 to the 9, 10 to the 11.5, and a wide variety of H1 gas fractions. So XGASS is beneficial for studying the Fall relation as it's not biased to H1 rich galaxies, and we have quite a large sample as well to look at. So to determine the stellar specific angular momentum, we use this equation here, which has two main parts. We have the surface density profile here and the velocity profile as well. So for the surface density profile, we use a Cercic mass profile for our study. So this is an example galaxy from XGASS, and we fit two component Cercic profiles using a Bayesian light fitting tool Profit. We then reconstruct magnitude profiles, where this galaxy in particular is a two-component galaxy, so there's a contribution of a bulge and a disk. And we have these for the SDS bands G, R, and I. We then use these to reconstruct a mass profile using the Zebedee mass to light conversion, or light to mass conversion, and that's what we use for our surface density profiles. The other component of a full relation is also a total stellar mass. So for this, we use we integrate the mass profile out to 10 RE to determine a total stellar mass. For the velocity profile, we assume a constant rotation curve. So because we want to have a large statistics, we turn to unresolved H1 velocity widths, which we get from XGASS. So we use the width of the H1 profile as our maximum rotation velocity, and we assume this to be constant for all radii. So the assumption is that the rotation curve is flat rather than curved, and we've done a bit of testing on this with mock data to see what effect this has on the specific angular momentum, and we actually find that this variation causes a difference that's less than the observational uncertainty we have, for example, in the light to mass conversion. And also, because we have unresolved kinematics, we can only assume either the bulge is co-rotating with the disk or it has zero rotation. So we have tried both of these and again find that it has little effect on our overall result, but I will refer to that a little bit more later as well. So to use the H1 widths, we need reliable H1 detections. So this limits our sample down to 564, as we have to make, obviously, H1 detection. The data has to be H1 detected. And then we also want to make sure that it's not confused and that it has an inclination greater than 30. And to test that this is still a representative sample, we've compared the mass size relation for our selected sample and the full XGASS sample. And we find that this doesn't bias our sample in any way. So this here is the full relation with the stellar mass shown here on the x-axis and the stellar specific angular momentum on the y. And this is for our total galaxies, so both the bulge and disk component of each of the galaxies. And you can see in the thin black line here, the best fit relation, and we find a slope of 0.47. Which is considerably shallower than a slope of 2/3, which, if you remember back to the start, is the relation you'd expect if the galaxies are following the same relation as the halos. Where here I show that as a purple dashed line, which is just fixing the slope to 2/3. The work that I mentioned earlier that also found a slope shallower than 2/3 was the Posty et al. 2018, and I show their relationship in blue here, where we are also a fair bit shallower than their results as well. We have the best agreement with their results for low stellar masses below 10 to the 10, and this is possibly due to a different sampling of morphologies, where we have mostly pure disk galaxies at these low stellar masses. So to investigate this further, we isolate just the disk components of our galaxies. We have bulge disk decompositions for all these galaxies. So we can isolate just the disk stellar mass and the specific angular momentum contributed by the disk. And here again, I'm showing the best fitting relation as this thin black line. And now we get a slope of 0.6, which is in much closer agreement to the Posty work, where their equivalent line for just the disk component has a slope of 0.58. And our slope is actually within error of theirs. We also still have the 2/3 slope line here in the purple dashed line. And again, we're in much closer agreement to this when we look at just the disk component of the galaxy. I should also mention that it's promising for our methodology that our normalization of our relation is also very close to that of the Posty work, where they used resolved kinematics in order to determine their specific angular momentum, whereas we obviously used unresolved. So this is promising that at least our methodology seems to be achieving similar results to resolved studies. So when we isolate just the disk component, we get a slope that's much closer to 2/3. So we thought, what would happen if we reverse that thinking and isolate just galaxies with a large bulge component? So this is what I'm showing here, where now I'm showing the total stellar mass and total specific angular momentum, but only galaxies that have more than 40% of their mass in the bulge component. So this limits our sample now to 100 galaxies. And here you can see our best fitting line again in the thin black has a slope of 0.69, which is now very close to the slope of 2/3 that you'd expect for the galaxies following the same relation as the halos. Like I mentioned earlier, we're assuming the bulge to be co-rotating with the disk, but if we do the other extreme assumption that the bulge is not rotating at all and fit a relation to that data, then you can get this red line here, where you see that the normalization of the specific angular momentum drops as you have less rotation in that calculation. But the slope of this doesn't change considerably, with only a slope of 0.75 now. So our result is still robust to this assumption, we feel. So we've seen that when you isolate just the disk component and the bulge component, or sorry, galaxies with a large bulge component, that you get a slope very close to 2/3, which is reminiscent of what I mentioned at the start with the full work, where you get parallel relations with slope 2/3 for varying morphologies. So we felt it was best to analyze exactly what was driving the scatter in our total for relation. So going back to the plot I had a few slides ago, this is again the total for relation of the disk and the bulge component combined. And we took every galaxy and measured its vertical offset from the best fitting relation and plotted that against different, so we've got bulge to total ratio here that we're plotting it against, as well as H1 gas fraction. I've got the running median shown here as the black line, with the grey is the error on the median. And you can see that there is a relationship between bulge to total ratio and the scatter of the for relation. In particular, for these red galaxies, which are high mass galaxies, there is quite a strong trend, whereas lower mass galaxies, particularly those with stellar mass less than 10 to the 10, they are mostly all pure disk galaxies where the fitting code hasn't found a bulge component, so they're clustered along here. Whereas the high mass galaxies, you have far better correlation with the scatter. In the H1 gas fraction, we also see quite a strong trend with the scatter, particularly now for the low mass galaxies though, which are shown here in blue. Whereas when you get to the higher mass galaxies, now your relationship with the scatter decreases. And this is probably just an observational constraint where H1 gas fractions are dominated by non-detections at high stellar masses. So it's harder for there to be variation in the H1 gas fraction. Whereas for the bulge to total ratio, it seems that we cannot distinguish bulge to total ratio for these low mass galaxies as there's no bulge detected. It's far better at tracing these higher stellar masses. So to summarize, when we look at these different for relations, we see that our work suggests that we have parallel relations, or at least close to parallel relations, with slope approximately 2/3 for a disk and bulge components. Whereas when we look at the total sample, we're not evenly sampling morphologies across stellar masses, which is then creating this slope that's less than 2/3. Just from the observational limits of not being able to sample morphologies evenly across stellar mass. So therefore, our results imply that we don't need to have this variation in galaxy formation theory in order to explain the slope of 2/3, less than 2/3. It can just be this observational constraint. Yeah. And also, because of these observational limits, we are better able to distinguish between these different morphologies with H1 gas fraction for the lower stellar masses and bulge to total ratio for these higher stellar masses. Thank you.